This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello everyone, welcome to Software Engineering Radio. My name is Felienne and today with me on the show I have Mike McCourt. Mike is a data scientist, but before he was an astrophysicist. He actually has a PhD in physics. He has worked at different universities in the United States where he studied galaxy formations. But he now works at a call analytics company called Invoca, where he designs machine learning models to help businesses categorize and understand their incoming phone calls. Welcome to the show, Mike.
Thanks so much for having me here.
So the topic of the show today is analyzing voice data. And as you might know, voice data really is everywhere. Like I have an Alexa at home and an Apple Watch. So talking to computers is actually not a thing of the future anymore. Many people do it now. But I don't even really know how it works. Mike, could you take us through the basic steps of how an Apple Watch knows the route to the nearest bus station?
Yeah, that's a great question. So the way that speech recognition works has actually changed quite a bit in the last few years. There's the traditional type of model that it's a statistical model called a hidden Markov model. Recently, there's been a move towards using a deep neural network to do speech recognition. I think the hidden Markov model is the easier one to discuss, but there are a number of steps, and the key idea is that words are not the fundamental element of speech. Words are actually made up of smaller components. I think they're called phonemes or phonemes. I'm not sure on the pronunciation. But the key idea is that, in the English language, at least, we have millions of words, but they're made up of a much smaller number of phonemes, a few dozen. And so the first step in speech recognition is to break up the audio stream into these phonemes, these building blocks of words. And I suppose the first step that you need to know in order to do that is some linguistic knowledge of how long does a phoneme actually last.
Yeah, so could you give an example maybe of what a phoneme is? Because I guess if people have never heard of it, it's a little bit abstract. What exactly is a phoneme?
Unfortunately, I'm not a linguist, so I may not give the best answer. They're sort of like letters. So like the word cat, I think, has three phonemes, the k, the a, and the t. Those are the building blocks that make up that word. But they're not exactly letters. I think English has 40, I think you told me there were 44 phonemes in English, and obviously we have 26 letters. But they're roughly the building blocks of words.
Yeah, sometimes I think also they can be two letters, like the P and the H together are the F sound in some cases. And that would be one phoneme because it's one soundy. I'm also not a linguist, but I think it's more or less the easy thing is like if it's one sound, then it's more or less one phoneme. If there are linguists in the audience, we're sorry for butchering your area of expertise.
Yep, my training is in physics, so... Yeah, so I think the first step that you really need to know is, well, how long does a phoneme last? If you're going to divide up the audio stream into these phonemes, you need to be looking on the right time scale. And so as the audio stream comes in, you chunk it out into segments that are overlapping. And then you want each segment to be short enough that it probably has just one phoneme in it, but long enough that you can actually capture the acoustic signature of a phoneme.
Okay, so step one is we have raw audio that you type, you speak into your phone or your Alexa or in the phone call, in your example, really over the phone.
Mm-hmm.
And then you divide that into phonemes. And then what is the next step?
Well, unfortunately, you don't know the phonemes yet. So you divide it into segments of time.
Mm-hmm.
But then you still have to figure out, you have to turn that audio into the phoneme. And so there's a transformation you do. In physics, we call it a Fourier transform, but it decomposes audio into the frequencies that make up that audio. And so if you were to do this on a piece of music, it would tell you what notes made up that music. Human speech is not quite made up of musical notes, but it's a similar idea. And then that gives you a acoustic signature for that small time window. And then that is a a signature that you try to match against a library of phonemes that you have.
Ah, I see. So first you're trying to guess which piece of audio could more or less realistically represent a phoneme in terms of the length of the piece of the audio. And then you match that piece against a known database of all those, the smaller set of phonemes that exist in English.
Exactly. Yep.
So then what happens if words sounds really the same, like 8, the number, and 8 as in I had something for dinner? For me, that sounds exactly the same.
Yep.
So how do you distinguish words with exactly the same sounds?
Yeah, so there's still two more steps. So you can take the audio stream, you break it up into these signatures of frequencies, you match those against phonemes. And then from the phonemes, you need to get to a word. And you use a pronunciation dictionary for that. But like you said, that the same set of phonemes could make multiple different words. And so on top of that, you have a language model. So, 8 the number or 8 the verb, those sound the same. But the words that come before or after can give you an indication of which one was the intention of the speaker. And so you have a statistical mapping from the audio to the phoneme. And that's never going to be certain because different people speak differently. They have different accents. They might have a bad audio connection, and so on. So that's a statistical connection. And then the mapping of the pronunciation to words is also statistical. There might be different ways to pronounce a word. And then which word choice is statistical because some words sound the same. And you have to determine from context what the most likely outcome is. And so you have these 3 probabilistic connections. And at the end of the day, you multiply those probabilities together. And you hope that the probability peaks at a particular word.
And then is the level of the matching only the word or the phoneme, or does it also take the context of the whole sentence or maybe even the whole conversation into account?
Yeah, so that last bit, like you said, distinguishing between 8 the number and 8 the verb, that's taking context into account. Ideally, you'd want to take the whole conversation as context because that's useful information, and you could use that to really, really nail down the probabilities. But that becomes too computationally expensive. So typically, you use a handful of words preceding that, maybe 4 or 5 words as context.
Okay, so it would be feasible and it might be better to take a bigger context into account, like the previous sentence or another call from the same person. But just because that's too expensive, you only look ahead or you only look back a few words.
Exactly, yeah. If only they gave us bigger computers.
Yeah, that would be nice. So, talking about taking context into account, what about accents? Like, as people know, I'm not a native speaker of English, and this is probably hearable for people. Is this also hearable for algorithms? Like, if my speech is processed, does my Alexa know? Oh, that's the Dutch lady again. We have to process her slightly differently.
They do. So it depends a little bit on how the model's implemented. So in all those steps that we laid out, there's actually tremendous freedom in how you design an algorithm to do that. Typically, because speech recognition has to be done really quickly, the algorithm for matching that acoustic signature to a phoneme, it's often a relatively simple one. People just use a normal distribution and hope that works. A normal distribution might work really well if everyone had the same accent, or if you were designing speech recognition for just one person. But if you have different accents or different people speaking, people with different pitches in their voice or so on, typically they're using the same phonemes to make up a word. The phoneme sounds a little bit differently when they say that. And so that complicates the relationship between that acoustic signature and the phoneme, that mapping. And so you have a choice in how you do the algorithm. You can implement a latent variable, which will actually try to figure out the accent of the speaker and their pitch and other characteristics of their voice and tune to that. Or you can design an algorithm that just tries to fit everyone, and that mapping is made complicated enough. The tent is big enough so that everyone can fit inside of it.
And which one would be a more successful approach? Is it better if you have a sense of what someone's accent is to classify that always in a certain case? Or is it better to just be very flexible and are able to analyze all sorts of different accents at the same time?
I don't know. I suspect that for performance reasons, most companies do the latter. They adopt a flexible model that can try to work for everyone. They might see better performance if that were tuned with a latent variable.
Yeah, you would think so. That if it's more precise, if it's zooming in more on your personal characteristics, it would be better. But maybe it's not. It's not feasible for performance reasons.
Yeah, well, and I think there's a trade-off. If the flexible model works well enough, then it may not be worth paying the performance penalty to tune it.
Yeah, fair enough. And what about other languages? Because Dutch is still sort of similar to English in the sense that we only indicate meaning with words, but a language like Chinese, there also tone matters for meaning. If you end a word in a certain higher pitch or a lower pitch, then the meaning might be different. Is that a thing that's taken into account from the beginning of the algorithm, or do you just still do the first phoneme matching steps, and then in the statistical analysis you then take into account the different pitches and tones in, for example, Chinese?
Yeah, I have to admit I know almost nothing about Chinese, so I don't know if the same notion of a phoneme works for Chinese. I suspect there's something analogous, and the same type of algorithm could work. I was actually trying to think of an example in English where tone or stress could matter. And the only example I came up with is the word invite. So if in American English, at least, if you say invite, we hear that as a verb. I'm inviting you to something. But now Americans will also say, I sent you an invite. And if you stress the first syllable of that word, we hear that as a noun. So that's an example where something other than the phoneme, in this case, the stress on the syllable, actually matters for the meaning. That was the only example I could think of in English. And fortunately for speech-to-text algorithms, invite as a noun and invite as a verb are spelled the same. So you'll never know if the algorithms got that right. But
Yeah, I know there's a paper about whether or not words are stressed, and the title of scientific paper, and the title of that paper is Stress Matters Revisited. So you can read that as Stress Matters Revisited or as Stress Matters Revisited. So that I also think is a very clever and interesting example of stress that matters. I really like that.
That's funny.
Yeah, so there must be more examples of where stress matters, but it's way different still than for Chinese. But sadly enough, you don't know all the details of that. So
No.
let's move on to the topic of why voice analysis is hard. Why do we have a whole episode of Software Engineering Radio dedicated to this topic? So what are some of the issues that you run into when you're analyzing voice data and you're trying to make it into textual data for further processing?
So fortunately for me, I don't actually do the voice-to-text part. I'm a consumer of this technology, not a producer of that aspect. But I think the key reason that it's hard is, as we said, there are 3 different steps you have to go through to turn the audio into a word. And they're all probabilistic. And so you never know what the right answer is. And you have to compute many different possibilities. And if you're using context over 5 words, you have to keep track of a huge number of different possibilities and solve for the probabilities of each. And then at the end, you figure out what your best answer is going to be. So it's computationally intensive, and it's hard to keep track of all those different possibilities.
And these different possibilities probably exist at different levels, right? So people are different, but also other aspects of how people speak might impact this analysis. Like if people are angry or if they're stressed, then that is an extra dimension of speech differences. Is that taken into account? That might be more interesting and more closer to what you are doing. Do you still get the emotion from the voice in the textual description? So if you get the output of the algorithm, does it say said in an angry voice?
Not the output that I get, although that would be interesting to play with.
Yeah.
Yeah, what I found, this often comes up on my team, and we're like, God, wouldn't it be so great if we could get the volume of the voice or the intonation?
Wow, yeah, volume is an interesting one also.
Yeah, so far what we've found is that language is incredibly rich, and the words that you use convey a huge amount of meaning.
Yeah.
And we're still not tapping all of that meaning. And so we've not yet felt the need to go into looking at volume and stress and intonation. We still have a huge amount of information that we're sitting on that we're trying to utilize more efficiently.
Yeah, let's zoom into the topic of what you actually do with voice analysis. So, as far as I've understand the work that you do, is you try to help companies classify calls that people make to their company. And also the classification is done automatically with machine learning models. Could you share a little bit more about your use case and the technologies involved in the use case?
Yeah, so we do call analytics for marketing. And in today's world, marketers are used to getting a lot of information about purchases that happen online. Right? So if you're reading the newspaper and you see an ad for something, click on the ad, go to a website, and buy something, they know exactly what ad drove that purchase. And they know that they can invest more of their energy into that advertising campaign. And that's become hugely important in the internet economy today. They lose a lot of that information when you pick up the phone. And so if you see an ad, but you don't click on it and buy online, you instead call the company and make a purchase. They don't know necessarily what ad drove that. And so they don't know how to optimize their advertising campaigns. So we work to do that, to provide attribution for purchases that happen over the phone. And then the team that I work on, we try to analyze what actually took place on the phone so that you're not optimizing merely ad campaigns that drove more calls, but you're optimizing for ad campaigns that drove calls for people who actually purchased something.
So, could you give a concrete example of some of that analysis? I find it hard to really to understand in a concrete sense what actually. Could you give an example of a phone call that you analyzed and the steps, the consequences the company took based on the analysis?
Yeah, so a really typical use case for us would be either a purchase or an appointment. So let's take the example of an appointment. If you're, let's say, a dentist's office in Santa Barbara, where I work, you might put out advertisements in a couple different newspapers. You've opened a new dental office and you're looking for patients, and you might put an ad in the New York Times, which has a huge readership all the way across the United States, and you might put an ad in a local Santa Barbara newspaper, and that has a much smaller readership, but they're people who are nearby. And if you track how many people are calling in from each advertisement, you might be getting many more calls from the New York Times ad because it has a bigger readership. But since those people are less likely to be in Santa Barbara, they're less likely to actually make an appointment. And what our software can do, or the software that I work on can do, is that it can analyze those calls and tell you whether an appointment was made. And you might find that even though the Santa Barbara newspaper is driving fewer calls, those people are more likely to make an appointment. And so based on that information, the dental office might realize that they should move some of their advertising money away from the New York Times and towards the local newspaper. So that's the goal of what we do.
Yeah, so some of the goals might be you listen to a call and you want to automatically detect, was this a call in which an appointment was made, or was this a call in which a purchase was made, so that you can then detect the source of an ad and the source of then a phone call. Is it more likely to lead to an ad or a purchase or an appointment?
Exactly. Yeah. We're helping businesses optimize how they run their business.
And how far does this go? Is it just a purchase was made, or an appointment was made, or is it also an appointment was made for, I don't know, a specific dental procedure that is more expensive and gaining more profit for the dentist? How specifically can you zoom in into the results of such phone calls?
So that's actually why analyzing phone calls is really tricky, is you quickly learn that there isn't just one type of appointment. There could be a first-time patient who has to be enrolled and they have to give a whole lot of their information to get into the system at the office. It could be a returning patient who's already in the system and it's a very short phone call to schedule an appointment. It could, in a dental office, it could be someone who's having an emergency, they're in pain and they want to get an appointment right away. So you quickly learn that there is no one type of conversation. People are so different that no two people who call in are going to have the same conversation.
Yeah, I guess that's what makes your work so interesting, because if it was all literally the same conversation, then no analysis would be needed.
Right?
So could you talk a little bit more about how that analysis works? Is this a supervised machine learning model where you have already access to lots of audio that has been classified by people, or is this just clustering based on similarity and no labeling is involved?
So we use a combination of supervised and unsupervised techniques. So at the end of the day, we're looking for something that's important to the business. And so they need to provide examples of exactly what it is that they're looking for. So, typically they might give us 100 examples of a call that's what they're looking for, and 100 examples of calls that don't reflect that. So for the dental office, they might give us 100 appointments and 100 calls that are not appointments. If we were to just train a supervised algorithm on that, we would really struggle, because those 100 calls that were appointments, none of them would be alike. And the 100 calls that were not appointments, none of them would be alike. And there might be some differences between the groups that we could detect, but it's pretty hard to do, because different people's wording is so distinct. And in a typical data set we have, there might be 40,000 words that appear in the vocabulary, just because different people phrase things differently and they have their individual voices. So with 100 examples, trying to learn the importance of 40,000 words, there's just not enough data to do that. So we use a combination of unsupervised learning and a supervised algorithm. And the key idea that we work with is that no two calls are going to be the same, because people have their individual voices and their own accents and dialects and their own personal needs. So they're not going to use the same sequences of words, but there are common themes that are shared and that run through the data set. And so we try to build a model that can find these common themes. And we do that by imposing layers of hierarchy. And so we say that on every individual call, they're totally distinct and they're totally unique, and that's fine, that's great. But we're looking for something that's shared. And one thing that we know has to be shared, if they're all speaking English or if they're all speaking Dutch, there has to be a dictionary of words that they're using. And if they're speaking a language, they have to be using the words from that language. So that's something that we know is shared, and we anchor the model on that end. So now we have something that's like too specific and too unique, where there's too much information to be useful. And then we have something on the other end where it's too general to be useful.
And that thing on the other end that you have that is too general is just the two data sets of appointments and no appointment. That's too general. And then just to summarize what you're saying, and then too specific is just the words that they use. And then you need something that's in the middle of those two extremes. Is that a good summary?
Yeah. So the thing that's too general is the dictionary, right? It's very basic, right? You're using words from a particular language.
Yeah.
And then we introduce layers of specialization. So we say, okay, well, then when you're making a call to a business, you're not going to use every word in the dictionary. There's only a small subset of those words that you use, and some words are more common than others. But the words that you use depend on the type of business that you're calling. And so there's a specialization of that dictionary. And that sort of now reflects an average phone call. And then we say, well, there's not just one type of phone call, there are many different types of phone calls. And so we model multiple specializations of that. And those kind of reflect the topics or the themes, the things that people talk about.
And then such models would always be specific for a certain customer or a certain domain, because the calls to a dentist are so different than the calls to, I don't know, a shoe shop, that those models always have to be tailored specifically towards a customer. Or are there parts of the model that you could always use for any sort of domain?
Yeah, I think that's what's really cool about this approach, where we lay out these levels of specialization, because it allows us to fit different types of data in a way where we say, these are related, but they're not the same. And so a shoe shop would have an appointment, and dentist office would have an appointment. And those are totally different. And the types of conversations that you would have might be totally different. But there is actually a lot in common between them. They are speaking English. That's huge. the patterns of words that are associated just with having a conversation about scheduling a time would be shared. And so this modeling approach that we take with these levels of specialization, that allows us to fit different types of data at the same time and borrow what's common among them, but still allow them to be different.
Yeah, so it's partly supervised and partly unsupervised, and partly domain specific and partly also domain independent and generic.
Yeah. So the unsupervised part is what allows us to extract these common themes, and then we use those to do the supervised learning. We're not trying to infer for all 40,000 words in the language what matters for an appointment. We're saying, okay, there were like 25 different themes that occurred on calls to this business. Which of those correlate with appointments? And then we can use that to make predictions, and that works much better.
So what do you exactly do with the predictions? So now you have a prediction. Is this live feedback to people who are on the phone with people that are making an appointment? Is it like, oh, this person is almost going to make an appointment? Quickly do something. How is this feedback used? Is this only meant as feedback about calls that have already happened to train marketeers to do better? Or is this live feedback?
Yeah, that's a conversation that we've had a number of times, and I think it would be really fun to try to develop that, live feedback to the people on the phone. I'm a little skeptical that we could tell them something that they don't already know. A human having a conversation is very good at figuring out what's going on, or at least they should be if they work as an agent on the phone lines. So for the moment, the main application that we use our software for is actually feedback to the marketers, and so that they know which advertising campaigns they're running are driving the most business.
Yeah, so the feedback isn't even at the individual customer level. It isn't to an agent like this call that we had. Well, our prediction showed it should have been an appointment, but you didn't get an appointment, so you did something wrong. It's
Right.
way more high level than that, where you just want to understand what type of calls lead to appointments, because that might be good ads or good sources of customers.
Exactly, and a lot of the companies that are our customers, they get thousands and thousands of phone calls a day. And so it would be very difficult for them to listen to phone calls and understand what's happening. So that they need a machine learning service like we have to cull through all of that data. And then they get that feedback in real time on the calls. And so that can be plumbed into bidding algorithms for Google Ads or keywords or however they choose to run their marketing campaigns.
So we talked a little bit already about why voice analytics is hard in general, but what is specifically hard about analyzing phone calls? Because of course that's not the same as me talking into my phone to Siri or to Alexa, but I'm calling on the phone. What are specific issues in that situation?
Yeah, that's something that we've really struggled with. A lot of the models, sort of off-the-shelf models that you can use for analyzing text, they're designed traditionally they've been designed for very clean data sets like New York Times articles or Wikipedia articles. These are relatively long pieces of text that have been edited and nicely written, and they're coherent and they have a point. Conversation is not always like that. Over the course of the phone call, they're figuring out why they called. Conversations can kind of jump from one topic to the next. And, also on phone calls, you have a mixture of natural conversation that's spontaneous and unpredictable. And that's why we have to go through all this effort to introduce these layers of hierarchy to look for common themes throughout the conversation. But you also have recordings. Sometimes you're sitting on hold and it's playing essentially an advertisement on the hold message. And there's no spontaneity there. That's the same from one call to the next. And then sometimes you have an agent who's reading a script. If you're scheduling an appointment at a dental office again, they have a series of questions that they ask. They might be reading that. And so you have these different levels of spontaneity in the conversation that make it quite tricky to make a model.
Yeah, I was going to ask, so is the first step trying to distinguish, is this someone reading a script? Is this informal, chatty-like conversation? Is that a first step to divide something into distinct buckets? Or is it more a spectrum of this is more towards formal and this is more towards lose?
Yeah, it would be great if we could do that as the first step. Because I would really like to ignore all of the scripted stuff and all of the recordings. Unfortunately, we're not able to tell, based on the words that are spoken, we're not able to tell what type of conversation it is until we've done our analysis. And so, the way that our code works, where we're looking for these common themes throughout the data set, but we recognize that every call might be distinct. We have information for each of those themes. We have information on how similar it is from one call to the next. That's part of the calculation we do to infer these themes. And so, as words come in and we're trying to figure out what themes they belong to, we can say, oh, this looks like it's one of those themes that's the same on every call. That's probably a recording. Or this looks a lot like an appointment, but all of the words that are interesting are spoken on the agent side. And so maybe the agent's trying to get someone to make an appointment, but they're not doing it.
Oh, yeah. So a question would be like, hey, do you want an appointment? Are you really not interested in an appointment? So then it's very much about appointment, but also it isn't because nothing is going to happen.
Exactly. And in some industries, the agents really try to upsell on the phone. And so there's a lot of conversation that, if you didn't know who was speaking, you'd be like, wow, they're buying everything. But it's not. It's just the agent is pitching, many different products.
Yeah. So I'm only realizing now that then also part of the trickiness of analyzing phone calls, different from analyzing chatting to Alexa, is also determining who is speaking. Is it sometimes the case that the voice of someone that's calling and the voice of the agent are very similar, and does that lead to problems? Or is it very easy to distinguish because you have different audio tracks, like different files from different sources?
So most of the time, it's easy for us because the phone data comes in stereo, and the caller's on one side and the agent's on the other side. So that's easy for us to distinguish. Occasionally, we have mono data, and then it's very hard to tell the speakers apart.
Yeah, that adds another step of all the things you are already trying to distinguish from each other.
Yeah.
So what about audio quality? I can imagine that if I speak into my phone and I'm not calling, or if I'm speaking to my Alexa in my home, that the call quality of the voice quality is sort of similar. But calling on a phone, if someone maybe has a really old phone or a really bad connection, is this something that interferes with your model? And how do you deal with that?
Yeah, unfortunately, over the phone, you have a huge range of call qualities. Some are going to be excellent and crystal clear, and you can hear every word, and the speech to text works great, and the transcript makes perfect sense. And sometimes you have someone, calling on their cell phone from the car on the freeway, and there's static, and the audio quality is horrible. And, the speech to text does the best that it can, but you end up with a transcript that's relatively garbled.
Yeah.
And one of the challenges in analyzing phone calls is you need a model that can handle both cases. So if your model is really sensitive to patterns, so that even in a really noisy transcript with bad audio quality, it can still pick out the relevant patterns. If you make your model too sensitive, then on a really good phone call, it might falsely trigger on words that maybe were said but don't indicate that you're making an appointment. Or
That is interesting. So better isn't always better, because better could also be too sensitive, and then also things go wrong. So there's like a sweet spot in the middle of sensitive enough but not too sensitive.
Yeah, and if the calls were a consistent quality, then it would be easy to pick how sensitive to make it.
Yeah, then you could do some manual calibration and then it would be okay.
Exactly, but they keep us on our feet. So they're different levels of sensitivity that we need to adapt based on the audio quality.
So you already mentioned some things that could go wrong, like you pick up words but they're on the agent sides, or you have too sensitive or too little sensitive models. What are other examples of stuff that makes your work really hard? Where do your algorithms get into trouble?
Yeah, another thing that sounds simple, but that was actually really a struggle for us, is that calls vary widely in length. So some calls are 2 hours long, and so,
wow.
Yeah, I've been there before, trying to return something to a business, and you get transferred many different times, and it takes a while to get to the right person. And some calls might just be a minute. If you're making an appointment, a dental office again, where you're already a patient. They just look you up in the system and they say, great, can you come in on Thursday? You say yes, and you're done. You have an appointment. So there's a huge range in length of phone calls. And again, there's a sensitivity issue where if a phone call is just a minute long, there may be only a few dozen words spoken, and you don't have a whole lot of evidence to base your prediction on. And so, you're working on just a handful of words that might be indicating that an appointment was made. But if you have a model that will predict on just a handful of words, well, in that hour-long call or 2-hour-long call, the likelihood that those words are going to appear is quite high.
Yeah, but then it doesn't necessarily say anything because in 2 hours, many words are going to be spoken.
Exactly, right? And you might think that the longer the phone call is, the less, as time goes on, it's less likely that they're getting what they want.
Yeah.
So one of the things that we had to figure out, which was actually kind of fun, I didn't realize this is what I was doing until I had the answer. I was thinking about it as like how to tune the model. And then once I had the number, I realized that what we'd done is we measured the efficiency of phone calls. And it turns out that if you're on a call to a business and you spend twice as long on the phone, you get about 60% more done. And so you have diminishing returns. And so I find that interesting. If you have 3 things that you need to get done on the phone, you're better off calling twice. Just call once, do 2 of them.
Yeah, just splitting up the length of the call. So you're analyzing things that are also interesting for people that call a call center rather than for the people that work at a call center.
Yeah, we're not selling that as a service at the moment, but
no, I understand. It's still a nice extra analysis.
Yeah, we could coach you on how to better interact with businesses.
So do you have any other things that go wrong? What else is very hard about this voice analysis that people... I'm also thinking of the next topic I want to ask you about. If our listeners also want to do this type of analysis themselves, what are definitely pitfalls that people should watch out for?
Yeah, so I think it depends on whether they're interested in doing the speech-to-text part, where they're actually analyzing the audio stream and turning that into text, or whether they want to do the stuff that I work on, which is extracting meaning from the text. They definitely have different pitfalls. The speech-to-text those are quite complicated algorithms, so I don't know how easy it would be to try to write one from scratch. But there are neat open source projects that provide frameworks for designing these types of models and playing around with it.
Could you give an example of some of those open source projects that people might want to check out if they do the speech to text?
Yeah, so one really neat one is called Kaldi. It's Kaldi, and it looks like it's a framework for designing these types of models. And so they provide different implementations of those algorithms. Like we talked about at the beginning of the episode, to do speech to text, you have to chain together multiple different probabilities. There's a connection between the acoustic signature and the phoneme, and then phonemes and words, and then words based on the context. And so they provide a framework where you can try out different implementations of these things and chain them together and try to make your own model. And then, the more modern, like as of the last couple of years approach, is to, rather than designing something based on these linguistic models, to try to use a deep neural network to sort of fit all of those probabilistic connections in one go. And Mozilla has an open source implementation of one of those neural networks. I've been meaning to try it for months now, and I haven't gotten to it yet, but I'm excited to.
Do you know the name of that open source framework?
It is, I think it's called Deep Speech.
Deep Speech. Okay, we can always look it up later and make sure that we put it in the show notes for people to use.
Yeah, I've been meaning to try that. It looks really interesting.
Yeah, that would be quite a different approach from the things you're doing now, because it's neural networks rather than, let's say, classical machine learning.
Yeah, I suspect that it's fundamentally doing the same things, but rather than having a linguistic expert divide the process into different chunks and you train separate models for each chunk, I think the idea here is to design an architecture for the neural network that can do that same series of tasks, but it learns them all simultaneously. And so you have some type of classifier that can look at that acoustic signature and map it to phonemes. And then rather than a hidden Markov model to model the sequence of phonemes and the transitions between them, you use a recurrent neural network for that. So I think it's a similar idea fundamentally, just a totally different way of training it and interacting with the data.
Okay. So if I hear you talk about all those algorithms, you say stuff like Markov models and deep neural nets. So suppose people in our audience want to also get started with these algorithms and these open source frameworks. What basics do you really need to know to work on this? Is it easy enough that you could just use something like that Mozilla framework, even though you don't really understand all the deep algorithms? Or do you really need to know some basics?
I think one of the neat things about these types of probabilistic models is they're often framed as generative models, and so it's a style of model that when you design it, you imagine you're designing something that could generate the data, and then essentially you fiddle with the parameters in the model such that the types of data that it would generate look like the data that you have, and that process amazingly, you don't need to totally understand the internals of the model. In the case of a neural network, you need to be able to take a derivative of the model output with respect to the parameters. And new software libraries like TensorFlow, they do those derivatives automatically. And so one of the really neat things about deep neural networks and deep learning today is TensorFlow has really allowed for a huge burst of creativity in designing these types of models, because you don't need to understand all of the internals and you don't need to code everything up explicitly. You can have this architecture and you can think about it at a really high level, and then TensorFlow sort of does the math for you. So I find that fascinating.
Nice. Yeah. So there isn't something you should specifically know or learn. You can actually just get started. But what would be some of the pitfalls? Something you in your expensive experience working with these types of algorithms? What are things we should have or be careful of? Do you need training data? Do you need calls that are longer than such and such? What are some things that would be requirements you would say? When is this going to be a good technology to try out?
For speech to text, you need a lot of data, and I think that's one of the real struggles with this. For the stuff that I work on, which is extracting meaning from the text, that I think is a much easier type of analysis to dive into on your own. Perhaps prejudiced because that's what I do, but I actually believe that. And I think there's a huge range of levels of analysis you can do, from very simple to very complicated. I think what I found really interesting, and what I think is one of the big mistakes that a lot of people make when analyzing language, is that they don't seriously consider the statistics of language and word choice. So a lot of off-the-shelf machine learning models, they implicitly assume that things follow normal distributions. It's not always explicitly laid out in the model, but it seems to be an implicit assumption in a lot of them. And word choice is really not normally distributed. So there's a lot of interesting patterns in language. One of them that I find amazing is called Zipf's law.
What is that?
Yeah. It's named for Zipf, Z-I-P-F, and he was a linguist, I think 200 years ago. And he started looking through, I think, the encyclopedia, and he tallied up how often every word appeared, and just counted, how often every word appeared. And he found that the most common word in English was the, and which makes sense. And the second most common word, I don't remember what it is, but the important thing is the second most common word appears half as often as the most common word. And the third most common word appears a third as often as the most common word. And the 10th most common word appears a 10th as often as the most common word. And so the word choice follows that kind of pattern. That's called a power law. And it's not at all like a normal distribution. It's a totally different mathematical function. And what I think is just magical about this, first of all, we don't know why word choice would follow that distribution. It's a very particular function, but it seems to be true. What's really neat is it was discovered for English, But people have since repeated the analysis for Spanish and for Dutch and for German and all kinds of, dozens of different languages. And they all have this property. And so there seems to be something fundamental about human language that has this property. And a lot of the natural language processing models don't take advantage of this fact. So I find that really interesting.
Yeah, that's really good to know, because you might want to apply algorithms where you think the normal distribution would fit, and then it doesn't, because it's the zip slot. What was the name again?
Zip, yeah.
Zip. Yeah, that's really good to know. Do you have any other of those specific things? Like, here are some things that are really nice to know if you want to use these algorithms.
Yeah, another really important one is that, again, a lot of machine learning models assume conditional independence. And so they assume that your probability of using a word might depend, either it doesn't depend on context at all, or it depends on a context of a few words surrounding it. But there's another phenomenon in language called burstiness, which is that if you say a word once, you're more likely to say it again. And so, we have a huge number of synonyms. You might have 10 words that you could choose from to express an idea. And the first time that you make your selection, that might be random. But then once you've explained something that way, you're going to keep using the same explanation again. And then if we're having a conversation and you explain something one way, I'm actually likely to pick up on your word choice and repeat it. And so there's kind of a rich get richer phenomenon in word choice, where once you start using a word, you use it more, and then you use it even more. And that also leads to something that's not normally distributed. Some words get all of the usage and some get almost none. But then in a different conversation, those might trade roles. And so there's really, really some interesting statistics underlying all these things. That's the part that I find really interesting.
Yeah, so it's a combination of knowing a little bit about machine learning models, like knowing the difference between supervised and unsupervised, and do you want to use a neural net or not, and also some specific knowledge on natural language processing, like how often words occur and how speech patterns of people in general work. So it's exactly at the intersection of those two domains where you at least need a little bit of knowledge before you can apply it.
Just enough knowledge to be dangerous. But I find it really fun, that cycle where you think about a phenomenon that you want to model, and then you have to think about, okay, well, how can I implement this in code? And, translating between those ideas and the math and the code. I find that to be really rewarding.
Yeah, and this is also, of course, a matter of understanding for what situation, what algorithm, what type of machine learning model would make most sense. How do you distinguish between one situation? What characteristics should a situation have where you say, this fits more a supervised machine learning model and more an unsupervised machine learning, or more a neural net? Can you help us decide, if we have this plethora of options of different algorithms, what type of situations which would be most useful?
So typically it depends on the task that I want to solve. Mm-hmm. So I think about the features that are important for me. So if I'm doing classification, for instance, I'm looking for words and phrases that indicate that something happened on a call. And then I will typically try to figure out what is the absolute simplest model that I could do, the simplest, dumbest thing I could do that would have the minimum needed to accomplish this task. And then I try to implement that, and I see how well it works. And then I try to beat that. And often that's really hard to do. So I would say start simple and get something working. And then you can see where it succeeds and where it fails, and try to understand what's leading to those failures, and then see if you can accommodate that into the model. But I think that the key for me is to always have that baseline to compare to, because it's really easy for me to come up with all these ideas and say, yeah, I'm going to fit for this and accommodate for this. And, I can have these wonderful ideas, but sometimes it doesn't do any better than the simple model.
So I think what you're saying is it is a little bit hard to know upfront. You should just try to start small and start simple, and then iterate from where you are then.
Yeah. At least that's the approach that I take. I find that it's easiest to do if you have a problem that you're really interested in. So the first text analysis thing that I worked on was about looking at authorship issues and trying to figure out who wrote a given document. There's a historical puzzle dating from the early days of the United States. There are a set of documents called the Federalist Papers, and they were written anonymously at the time, but we now know that they were written by Alexander Hamilton and James Madison, who went on to become early presidents of the country. And some of the papers we know were written by Hamilton, and some of them we know were written by Madison. And then there's about a third of the papers that have been disputed. And so over the years, there have been a number of people who've tried to, definitively say who wrote which ones. And for the most part, those different analyses have not agreed. So when I was first getting into machine learning and doing my career switch from astrophysics into data science, I came across that problem and I thought, well, this would be really fun to see, if I can design a statistical model based on word choice and word usage to try to make this determination. So that was kind of my entree into this field. And I had a problem that I was really interested in, and I really wanted to know the answer. And I wanted to see how well I could do on this. And again, I started simple and started trying to make these predictions and comparing them with what different historians had said earlier.
And did you find anything new with your algorithm that historians didn't find?
My conclusion was that Madison had written almost all of the disputed ones. So historians have gone in cycles where over some periods they think Hamilton wrote most of them, and some periods they think Madison wrote most of them, and so on. So there tend to be these waves. My analysis agreed with the Madisonites.
Interesting. And we will probably never know exactly. So who is right, we might never know because we were...
Well, of course I'm right.
Oh, yeah. The algorithm must be right, of course. I'm sure a machine learning algorithm is better than people that actually are. On that note, that actually was everything I wanted to ask you. Is there anything you wanted to share before we close the interview?
No, I think you pretty well covered it.
Nice. So one more question we always ask our guests is, where can we read more about you, about your company, about the work you do? Do you have any links for us to put in the show notes?
Yes. The company is Invoca, INVOCA. And we have a company blog, and then our engineering team for software engineers and data scientists. We also have a technical blog.
Nice. We'll make sure that we add the links of all of those blogs to the show notes so people can check it out and learn more about what you do and how you use the voice analysis algorithms to do so. Thanks so much for being on the show, Mike.
Oh, thank you very much.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.